So there are two things we're going to do today. First is to discuss and talk about the paper for the first three questions. So I ask you to make a note, post on Moodle so we can go through that as well. And then the second part will be some exercise to do before the midterm on Thursday. Okay. All right, so what we're going to do is we're going to look at question by question. And I will give you time again to talk to your neighbors. And you're welcome to open up Moodle while you're doing the discussion. Because I think many of the responses from you are really good to use as discussion material. And all right, so the first question is, how does the paper, not the paper that we read, but the first paper, Gelfand and Smith, 1990, suggests you obtain an approximate sample from the marginal distribution of fx. How is it different from or similar to the approach that we talked about in class, mostly from last week, and discuss the advantages and disadvantages of each approach. I think there are about 5 responses to this on Moodle, so feel free to browse them while you're doing the discussion, and then I will just ask for people to talk about in class, especially discuss the difference and similarity, and then the advantages and disadvantages. Okay? So take your time, talk to your neighbors about this. And yeah, also just mute your mic if you're not speaking, and that will be helpful. And we're gonna spend a few minutes on this, talk to your neighbors about your ideas. Some of the responses are correct, some of them are not entirely correct, so make sure that, which is fine. Yeah, totally fine. I think that's what the discussion is more. Yeah, so, but yeah, take your time now going through them and then talk to your neighbor about your thoughts. And yeah, so as you're discussing, I just want you to maybe just write down a couple of comments or like the points to talk about. I know some of you are talking about computing or like the computation time. So that will be something worth looking at, I guess, especially the speed, and then compare the advantages and disadvantages of the two methods. Okay, so that will be one thing. And also, I guess another thing is about how independent those laws are. So that will be another angle of discussing the disadvantages and advantages. Okay? So yeah, I think that's all. Yeah, I'll give you a few more minutes to finish the discussion, but keep in mind about those ideas as we're doing your discussion. Okay, I think I would just ask for whoever wants to talk about maybe just first, summarize what Gelfand and Smith suggested to do. Anyone? What do they suggest to do when to obtain an approximate sample from the marginal posterior distribution? Yeah, Karen.
So instead of just taking one chain like we did in class, they suggest doing m different chains and then just saving the last value in each chain. So if each chain has length k, just saving the kth value and making a sample from those kth values.
So each chain has length k, so the last kth value. Then, so that means once you are done with your sampling, you have m different values.
Yeah.
Okay. That makes sense? Everybody agrees? Okay. So I guess as Caroline was talking about in our class, what we were talking about is we run a super long chain, and then we do certain things, right? Like say we do burn in when we want to get rid of the effects of the influence from the beginning or initial values. So we do burn in, and even just among the ones that we don't burn in, we also do something called thinning. Remember, trying to get rid of the autocorrelation among the draws. Okay, so what they do is they run m different chains, and they only save the last one. So I guess you will be more independent in some sense. That you don't even need to do the thinning. You don't even need to look at the autocorrelation functions to get them. So I guess that's the differences and similarities. So now if we move to the advantages and disadvantages, yeah, anybody wants to talk about it? Either just the approach from Gelfand and Smith, or our approach, or just compare them directly.
Yeah, we were saying how the computing time problem be a lot longer with Gelfand and Smith because it's kind of taking our approach and doing it, 500 times or however many observations you might get. Once.
All right. right, so let's stay here for a little bit. So Lena's point is Gelfand and Smith will take longer because they have to say if m equals to 500, then they will have to run 500 times of what we do. Do you agree or not?
Well, if you're trying, depends on the thinning, like how much you're thinning and how much you burn out. There is certainly a case where like it could be computationally more intensive to do what we were describing. But I think it's more likely that it's computationally intense. Well, it depends on the situation.
Right, so I think the goal is that we want to get a certain number of draws, right? Let's say, I don't know, let's say we want to get, 1,000 draws in total, let's say, and we want 1,000 independent draws. Okay, so what you would do in the case for the Gelfand and Smith, if the goal is to get a total of 1,000 draws, you will have to run 1,000 different chains, right? So for Gelfand and Smith, what you need to do is that your m is 1,000. But of course, another thing that I guess not clear at the moment is how large the k should be. So for each chain, you still need to run it long enough for it to converge, right? So even though, yes, like among the chains, across the chains, they're all independent, but you still want to have independent draws that is already in the ballpark of what the posterior distribution should be. So if that is the case, your k probably wouldn't be too low. In fact, if we later look at the paper a little bit more, I think they talk about k to be 10 or 20, and that would be something actually to keep in mind whether that will be sufficient or not. In simple models that they're doing, maybe not so bad, but if you have complicated models, when you're running so many independent separate chains, your k might not be low, and then that will just bump up your computation time a lot. Okay, all right, so for us, if we want to get the total, I would just say our. If we want to get a total of 1,000 independent draws, what should we do? Like generically, say for a Gibbs sampler, if we want to have independent 1,000 draws, in our approach, what would we do?
Well, we would just like burn a lot and then employ thinning, like take like a large number of draws from the one chain, and then once we like look at the graph and see that it's converged in a certain region, just like draw those 1,000 from that region.
Yeah, so if we use the same notation m, our m is always 1, right? We round it super long. But our k, well, it depends on how big the autocorrelation will be. Let's say if it's 10, and I want to do a 50% burn-in. So that means I will need to have, what, 1,000 times 10? That's only getting the samples that I have. Like I'm thinning every 10th draw, and I'm getting 1,000 times 10, which is 10,000 draws after the burn-in, right? And then I need to time 2 in order to finish the whole chain running, okay? And of course, that highly depends on this value of 10, because sometimes 10 might not be enough. So what they do is for the Gelfand and Smith is they're already running independent chains. So in that case, they don't do thinning, so they don't have that as something like lagging behind, right? Whereas for us, we have to check the autocorrelation function to see how badly the autocorrelation is. If it's not too bad, then maybe 10 is enough. If it's highly correlated, you might have to do 50, right? Or even 100. So that would just bump up how long you have to run for your own single chain.
Y times 2.
Yeah, so I was saying if you're doing a 50% burn-in.
Oh, okay, sure.
Yeah, that's what it is. Yeah, but this is just like generically like how long it will be. And of course, for the Gelfand and Smith, we just don't know how long the K will have to be. For complicated models, 10 is definitely not sufficient. Okay, I think in the paper they discussed simple cases, the beta binomial, which we can discuss in a minute as well for question 2 and 3. I think that's what A equals to 10, I think for figure 1. And their m is 500. Okay? So all of those together will be important thing to think about in terms of, well, maybe for some cases there are certain advantages using one over the other. Maybe in some other cases you might want to use the other one. But I do want to mention that how independent those draws are. That's definitely important because that's what we want to use to summarize our posterior. Okay, so that's the goal. I mean, sometimes even if it's going to run much, much longer in one situation, but it will guarantee independent draws, we might just go for it. Okay, and I should also mention what they talk about, m equals to say 500 or 1,000, like what we were talking about. Their approach, you can also parallel your work on on clusters. So in some cases, if you have pretty powerful computing resources, it might not be a bad thing. Okay, because at the end of the day, each of the K I think will be shorter because they don't do burn-in. They only care about the last draw. Okay, so independence I think is the first most important criteria, and then you think about computing time. Okay, but I think going through this, especially the current practice, what people usually do, like one long chain and then do the thinning. And so Gelfand and Smith, 1990, that's the first paper when people propose Gibbs sampling. And the paper that we're reading is 1992. That's, as you could imagine, especially in their abstract and introduction, they mention about like how people may have some misunderstanding about how this practice is doing all that. So this is a pretty early but accessible paper talking about the Gibbs sampler, the foundation of it, as well as how the like their recommended practice. Okay, but as you can see, things might change. This is almost like 30 years ago. So nowadays we can do a long chain and just do thinning, but you're also welcome to do multiple chains. I think last time we were doing the MCMC diagnostics, we saw how to use JAGs pretty quickly in order to set the number of chains, right? And then you can check all of the convergence and stuff. So that will be something else good to keep in mind. Okay. All right, any comments, additional comments on this before we move on? Great, so if not, I think 2 and 3 are sort of related. So how about let's start with question 3 first, because this is comparing the two figures, and then we come back to question 2 about the plane of the conditional densities. So focus on question 3. If you look at the 2 simulations that they did in the 2 figures, figure 1 and figure 3, and I want you to talk to your neighbors about your thoughts, the similarities and differences between the 2 plots, especially what they're summarizing, and is there any differences in the way that they compute the marginal density, okay? And also just why the conditional carries more information than the marginal based on your comparison between figure 1 and figure 3. So take your time and chat with your questions. Okay, let's hear from some of you. Even if you have further questions, feel free to raise them up so we can talk about them. So figure 1 and figure 3, they did 2 simulations. And I guess to start off, they have the black and white in their plotting, right? So the white histograms in both of the cases, they are the exact solution. Okay, in a sense that if you go to equation 2.7, you will see that this beta binomial. So this setup is, I guess, x given y is binomial. I think in their notation in y. Yeah, so y in this case is like p, the proportion in the situation, and then y given x will be a beta of their notation x plus alpha and minus x plus beta. Yeah, so this is the actual Gibbs when they're doing the sampling step by step. And you will see in their equation 2.7, so even though you can write, so pretty much you can write the joint of x and y, and then you can actually integrate out y in order to get the margin of x. So what they tell you in equation 2.7 is that fx actually follows what they call a beta binomial distribution. So keep in mind that this is different from what we usually talk about. In the past, when we're referring to beta binomial, we're talking about the binomial data model with a beta prior. Okay, that's the conjugacy that we're talking about. This is a new distribution that they're talking about. So that means the marginal distribution of fx is analytically available. That is a known distribution. So I think the white bars in both of the figures are the draws directly from this beta binomial distribution. Okay, so what they're using the white bars for is the black ones in two figures. They obtain them in different ways, but the white ones I think are the ones that you should use as a benchmark to compare to. Okay, because the closer the black ones to the white one, the better the approximation. Okay, so keep in mind that the white ones, they are the exact solution. All right, so what's the black bars being plotted in figure 1? Anyone? When they described it, what are they trying to plot? Yeah.
So figure 1 is plotting x1 up to xn, as opposed to figure 3 that is plotting the density of x given y, simulated y value.
Yeah, so this is the first difference if you look at the two figures. So figure 1, as you can see on the y-axis, is the count. And so they're plotting the count of the observations falling into each of the categories, whereas figure 3 is density. So that's why you can see that the y-axis of the figure 3 goes from 0 to 12, like 0.12. Okay, so that's a density, that's a probability in this case, PMF. Whereas for figure 1, it's the count itself. Okay, all right. So those are the differences. Any other things that worth noting? Which has a better approximation based on your evaluation? Figure 1 and figure 2.
The second one.
The second one? So I guess overall we do see a closer matching in terms of the two different colors of plot. So why do you think that is the case? So actually, yeah, before we get there, maybe, so the first difference is that figure 1 is plotting counts, whereas figure 3 is plotting the density, okay? But how did they get the density in figure 3 based on your reading? They talk about those conditional and then taking the average. So how do you understand their approach in terms of plotting up figure 3?
So they've done a bunch of different Gibbs sequences, and then they've pulled like a sample from the last y value for each of those Gibbs sequences, and then they basically took the average of p of x given each of those little y's, and they kind of shown that that's a good estimation of the marginal f. So that was the strategy for figure 3.
Yeah, so good point. So Kobe's point is you can see that. So figure 3 not only uses, so the goal is plotting x. Okay, x is, so they're x and y, but we focus on x looking at the margin, trying to approximate the marginal posterior. So figure 3 not only uses x, but also uses y. Okay, so we know that we're doing this iteratively, like we generate x given y and then y given x until the last point, right? So we do this iteratively, so meaning that in each chain that you're doing your Gibbs sampler, you're gonna have a sequence of x and sequence of y. So in figure 3, what they're doing is that at the last iteration, I take a look at my y's as well, right? So if you look at equation 2.11, they have this p hat, x equals to x, so there's 2.11 here. They're taking the average of, so m is the number of sequences that you're doing, MCMC Gibbs sample you're doing. So what they do is they evaluate the value of x, the PMF of it, even, I guess, just the second last draw of your y, that your last draw of x is depending on. Okay, so they utilize this as well. So pretty much for each iteration, shouldn't say iteration, for each Gibbs sampler sequence, they look at, so that's the index of I here. They look at the last one, and then they're using the last y value in terms of thinking about averaging the density of each of the x values. So that's the key difference, because if you now go back to figure 1, you will see that, well, they are simply, so they also round. I mean, I think it's the same round that they were doing. They do 500 rounds for a length of k using n equals to 16, alpha 2, and beta 4. That's the same setup, but they summarize things differently. Okay? Figure 3 is looking at this density average given the values of last y, whereas your figure 1 is simply just looking at, well, pretty much counting the empirical counts how many, say, values of x fall into each of the little integer interval that they're looking at. So that's why for figure 1 it's counts, whereas for figure 3 it's probability or density over here. Okay, so based on this, I guess why the conditional carries more information than the marginal. We know that figure 3, using the conditional, average of the conditional, we can get a better approximation. Would that be sufficient to say that the conditional carries more information than the marginal? What do you think? Or maybe together, keep this in mind if we come back to question 2 here. It's related in some sense that the authors claim Gibbs sampling can be used to estimate the density itself of averaging the final conditional densities from each Gibbs sequence. I think that's just what we did. We discussed about figure 3, right? How do they do it? So what is the theory behind this claim? And I guess the last part we already answered it. How does figure 3 support this claim? So I'll give you a couple of more minutes just to think about why this works. We can already see that from figure 3 it's getting a better approximation. So why do you think it's working? And the paper does talk about certain theory behind this claim. So what do they talk about? Okay, so what are your thoughts from the paper? Where do they discuss why you can do this? And if there's a particular theory that they mentioned that can support this claim. Yeah.
They're kind of like, so I think equation 2.9 is a, 2.10, sorry, where they say that the expectation of the conditional probability is equal to the marginal, and then they kind of try to mimic the expectation by taking the average of the marginals.
Right.
And figure 3, I think, really supports it because the white is the actual marginal probability distribution of x, and then we can see how when we take the average of the conditionals, it almost perfectly mimics that.
Right. Yeah. And I should also mention, I think, in the paper when they, so right before section 3, they have this paragraph talking about how we can think of, like how to summarize or evaluate the characteristics of this marginal of fx. So figure 1, what they're doing is you can get the, for example, the mean, I guess, of fx to be 1 over m times the sum of all of the xi that you get. Okay, so these are the actual draws that you get from each of these. So there are m draws in total. I'm just taking the average. So that's what figure 1 is doing, and that's directly using the marginal, right? However, if you keep reading that paragraph, you will see that they talk about in figure 3, a better estimate is this 1 over m. You still summing over m terms, but each term now is the expectation, like what Nina was saying, from equation 210. So let me make sure this is capital X here, sorry. Yeah, so they say as long as this expectation is obtainable, this will be a better approximation. Okay, so they mentioned that this is supported by this Rao-Blackwell theorem, so don't worry too much about it. You don't have to go back to the original paper to read about it, but I think it's important for us to see why figure 1 and figure 2 are doing what they're saying here, and also comparing figure 1 and figure 2, like what figure 1 and figure 3, sorry, as what we just did, is supporting what they're saying here. Okay. So as long as the expected value, so this is exactly what we were doing earlier, that we're relying on the draws of y that we have in the chain as well. Okay. Whereas for figure 1, you only use the draws that you have from the x, and then this is a way to justify that using the conditional expectation, if you have them, will be a better approximation. Okay. I should mention, I think in practice, especially based on the ones that we've been talking about, we're probably just using figure 1 or that approach in figure 1, because we're looking at the draws that we have after the burn-in, after the thinning, and then we just plot them, right? They're almost independent, and we're using that to approximate the posterior distribution. Okay? But you can see that if you look at simple cases like this, and then if you get into the details to plot and then generate all of the Gibbs samplers that you have, you will see how the different effects will be. And in fact, I think lab 3 will be on replicating those graphs. So you will get into the actual inner workings of how to make sure that you know how to do the Gibbs sampler in the first place, is beta and then binomial, the two conditional posterior, full conditional posterior distribution, and then try to make your summary based on figure 1 and figure 3. Okay, so I will, yeah, I think it will be sometime maybe next week before the break or even after the break to see when we will be able to finish the other stuff, but that will be the topic of lab 3. Okay, all right, so there are 4 other questions which will be left for next week, because this Thursday will be the midterm exam. So next Tuesday, we're going to discuss the other 4. So I will also just ask you to make one response to any of those questions before the class, and then we will have the same format in terms of the discussion. Okay. All right, so